An X-class solar flare just fired 1 billion tons of plasma toward Earth, and while you slept, aviation authorities made a decision that should terrify you. 6,000 aircraft grounded, not for weather, not for mechanics, for something invisible racing through space at 4 million miles per hour. Remember that JetBlue flight that plunged without explanation? Passengers felt weightless, oxygen masks deployed, chaos in crystal clear skies. That wasn't an isolated incident. It was a warning shot. The sun has entered its maximum phase, and our technology, our GPS, our very ability to navigate the skies is built on assumptions that no longer hold. What happens next isn't speculation. Stay with me, and I'll show you why experts are warning we are unprepared for what comes next. You'll want to stay close as solar maximum approaches its peak and the warnings from experts grow more urgent. Subscribe to follow this unfolding crisis, because each X-class flare peels back another layer of our false sense of security. Now, let's dim the lights and dive into this cosmic mystery together. Picture this for a moment. You're scrolling through your newsfeed, and every other headline screams about some mysterious interstellar visitor. 3-Eye Atlas, they call it. A cosmic wanderer from beyond our solar system, triggering 1,000 conspiracy theories and twice as many YouTube videos. Everyone's looking up, pointing telescopes at the sky, asking if we're alone, if something's coming, if this is the big reveal we've all been waiting for. Meanwhile, 93 million miles away, our own star just detonated what amounts to a cosmic bomb, and almost nobody noticed. Not until the planes started falling from the sky. I'm not being dramatic here. Well, maybe a little. But here's what actually happened while you were busy reading about interstellar objects. On November 11th, 2025, a region on the sun's surface designated AR 4274 unleashed an X 5.1 class solar flare. The strongest eruption of 2025. The kind of event that makes solar physicists sit up straight in their chairs and reach for their phones. This wasn't some minor hiccup in our star's magnetic field. This was the sun's version of snapping a steel cable under tension, except the cable was made of plasma hotter than anything you can imagine. And when it snapped, it launched billions of tons of charged particles toward Earth at over 1,500 kilometers per second. You know what happened next? Radio blackouts across Africa and Europe. Satellites going into safe mode. GPS systems flickering like dying light bulbs. And then, if the whispers are true, something unprecedented. Roughly 6,000 Airbus A320 aircraft grounded. Emergency software updates, they said. Radiation-induced fly-by-wire errors, they whispered. Which is a very technical way of saying that someone, somewhere, realized that modern commercial aviation had just become vulnerable to something we can't see, can't predict, and definitely can't stop. Let me paint you a picture of what we're actually dealing with here. Every single system that keeps modern civilization humming along exists in a delicate bubble. Your smartphone works because satellites overhead are talking to cell towers. Your bank account exists because computers are synchronized down to the nanosecond using GPS timing signals. That airplane you're about to board, it flies because computers are making thousands of calculations per second, adjusting control surfaces, monitoring systems, keeping you alive at 35,000 feet where the air is too thin to breathe, and the temperature would freeze you solid in minutes. All of it, every bit of it, depends on electronics that were designed in a world where we thought we understood the rules. But here's the thing about cosmic radiation. It doesn't care about your design specifications. It doesn't care about your redundancy systems or your backup plans. A single high-energy particle, traveling at nearly the speed of light, can punch through the fuselage of an aircraft like it's not even there. It can hit a computer chip, flip a single bit in memory from a 1 to a 0 or vice versa, and suddenly your flight control computer thinks you're upside down when you're right side up. or that you're climbing when you're diving, or it just stops thinking altogether. You want to know the scariest part? We're not talking about science fiction. We're talking about something that allegedly already happened. Flight data from what's being called the JetBlue Clear Sky Plunge. An aircraft reportedly dropped 25,000 feet in seconds. Not during a storm, not during turbulence, during what pilots call severe, clear, perfect flying weather. One moment, everything's normal. The next, the plane's in an uncommanded dive, instruments going haywire, passengers screaming, pilots fighting for control. And here's the kicker. It happened on a day when solar activity was supposedly quiet. No major flares, no coronal mass ejections, nothing that should have caused problems. So how do you explain a catastrophic electronics failure on a commercial aircraft during a quiet day? You start asking uncomfortable questions. Questions about cosmic rays. Questions about ground-level enhancements. Questions about whether we've built a global civilization on technology that's fundamentally vulnerable to forces we barely understand and definitely can't control. Questions that lead you to wonder if maybe, just maybe, we've been looking in the wrong direction this whole time. Because while everyone's been obsessing over whether some interstellar rock might be an alien probe, the real threat has been staring us in the face. Literally. You can see it every morning when you wake up, assuming it's not cloudy. That big yellow ball in the sky, it's not just a light source. It's a fusion reactor converting 4 million tons of matter into energy every single second. It's a churning ball of plasma with magnetic fields that could swallow Earth whole without noticing. And right now, it's angry. We're in what scientists call solar cycle 25. The sun goes through these cycles, roughly 11 years each, where its magnetic field flips and all sorts of chaos breaks loose on its surface. Sunspots appear and disappear. Flares erupt. Coronal mass ejections blast billions of tons of material into space. And right now, we're at or near the maximum of this cycle, which means more flares, stronger flares, more frequent coronal mass ejections, more chances for something to go catastrophically wrong. Think about what that means for a civilization that put all its eggs in the digital basket. We've built a world where electricity flows through millions of miles of power lines, all synchronized to within microseconds. Where satellites orbit overhead in a cosmic shooting gallery, getting pelted by radiation 24/7. Where aircraft fly higher and faster than ever before, through layers of atmosphere where cosmic radiation is stronger. Where every car, every phone, every computer depends on microchips with features measured in nanometers, so small that a single particle can cause failures. And here's what keeps me up at night. We act like we're prepared for this. We have space weather forecasts. We have radiation monitors. We have protocols and procedures and backup systems. But do we really understand what we're up against? Do we really know what happens when multiple coronal mass ejections hit in succession? Or when a ground-level enhancement pumps high-energy protons into the atmosphere? Or when some combination of factors we haven't even thought of creates a perfect storm? The answer, I think, is no. We don't know. We're learning as we go. And sometimes we're learning the hard way. Like when thousands of aircraft get grounded because someone realized that maybe, just maybe, flying computers through a cosmic radiation environment wasn't as safe as we thought. Like when satellites fail earlier than expected because space weather is more severe than the models predicted. Like when power grids experience unexplained anomalies that engineers can't quite figure out. So here's what we're going to do over the next hour or so. We're going to look at what actually happened during that November 11th flare. We're going to examine the science behind solar storms and cosmic radiation. We're going to explore whether modern aviation really is vulnerable in ways we didn't anticipate. We're going to ask uncomfortable questions about whether human technology might actually be making things worse. And we're going to consider the possibility that we're not nearly as prepared as we'd like to think for what comes next. Because the sun isn't done with us yet. Not by a long shot. And while you were worried about visitors from other star systems, the real cosmic threat was already here. Already striking. Already exposing just how fragile our modern world really is. Let's get into the details of what actually went down, because this wasn't just any solar event. This was the kind of eruption that makes you realize we're living on a very small rock next to a very large bomb that goes off on a regular basis. November 11th, 2025. Active region 40. 274 had been acting up for days. If you'd been watching the sun through proper filters, which I hope you weren't doing without professional equipment, you would have seen this dark patch on the solar surface, a sunspot group. These things are cooler regions where intense magnetic fields punch through the sun's surface, and they're where all the action happens. AR 4274 wasn't just any sunspot region. It was primed, loaded, ready to blow. The numbers tell the story. November 9th, an X-1.7 class flare erupted from this region. That's already a significant event. X-class flares are the big ones, the heavyweight champions of solar eruptions. The 1.7 means it released energy equivalent to 1.7 times the baseline X-class threshold. That's a lot of energy, enough to ionize the upper atmosphere, disrupt radio communications, send satellites scrambling. But AR 4274 wasn't finished. Not even close. November 10th, another blast. X 1.2 this time. 2 major eruptions in 2 days from the same region. Solar physicists were paying attention now. This kind of clustering behavior, where a single active region repeatedly explodes, tells you something about the underlying magnetic structure. It's like watching cracks spread across a windshield. Each one releases some stress, but the fundamental instability remains. The magnetic field is twisted, sheared, loaded with energy that has nowhere to go but out. And then came November 11th, the big one, X 5.1. Let me give you some context here. The X-class scale is logarithmic, which means each whole number represents a tenfold increase in energy. An X2 is 10 times stronger than an X1. An X5 is 100 times stronger than an X.05. This wasn't just a solar flare. This was the sun screaming. When that much energy releases in a matter of minutes, things happen fast. The flare itself is electromagnetic radiation, traveling at the speed of light. 8 minutes after it left the sun's surface, it slammed into Earth's atmosphere. The sunlit side of our planet, which happened to be Africa and Europe at the time, experienced immediate radio blackouts. High-frequency communications, the kind used by aircraft and ships and emergency services, just stopped working. The upper atmosphere became ionized, a charged mess that radio waves couldn't penetrate properly. But the flare was just the opening act. What came next was worse. Coronagraphs on satellites like SOHO caught it happening in real time. A coronal mass ejection, a CME, erupting from the same region. Imagine 1 billion tons of solar plasma and magnetic field getting hurled into space like a cosmic fastball. Initial velocity estimates put it at around 1,500 kilometers per second. That's fast. Really fast. For context, that's about 0.5% the speed of light, which sounds small until you realize it means this cloud of charged particles was going to cross the 93 million miles between the sun and Earth in less than a day. Now here's where it gets interesting. A coronal mass ejection isn't just a cloud of gas. It's a self-contained magnetic structure. And when it hits Earth's magnetic field, things get complicated. Earth has a magnetosphere, this invisible bubble of magnetic field lines that normally protects us from the solar wind. It's like a force field in science fiction, except real. But when a CME hits, especially a strong one traveling fast, it can compress the magnetosphere, breach it, inject particles into the Van Allen radiation belts, and trigger what's called a geomagnetic storm. The consequences cascade from there. Satellites in orbit suddenly find themselves in a more hostile radiation environment. Some go into safe mode automatically, shutting down non-essential systems to protect their electronics. Others aren't so lucky. The increased particle flux can cause charging effects where different parts of a spacecraft build up different electrical potentials, leading to sparks and failures. It can cause drag on low Earth orbit satellites because the upper atmosphere heats up and expands when this stuff hits, creating more resistance. On the ground, effects vary. Power grids are particularly vulnerable because they're essentially giant antennas. When the magnetic field fluctuates rapidly during a geomagnetic storm, it induces currents in long conductors, like the high-voltage transmission lines that carry electricity across continents. These geomagnetically induced currents can saturate transformers, causing them to overheat or fail. In extreme cases, entire grid sections can go dark. It happened in Quebec in 1989. Could happen again. But here's what most people don't think about: GPS. Every satellite in the GPS constellation is up there broadcasting timing signals accurate to within nanoseconds. Your phone, your car, your aircraft navigation system, they're all receiving these signals and using them to calculate position and time. When the ionosphere gets disturbed during a solar storm, those signals get delayed, refracted, scattered. The timing gets wonky. Position calculations become unreliable. And it's not just navigation. The modern power grid uses GPS timing signals to synchronize generators and switching equipment. Cellular networks use them to coordinate towers. Financial systems use them to timestamp transactions. When GPS goes fuzzy, lots of systems start having problems. Now imagine you're a pilot at 35,000 feet when all this is happening. Your radios might be crackling with interference or dead entirely. Your GPS navigation is showing errors or maybe just stopped updating. Your electronic flight instruments, which depend on multiple computer systems talking to each other constantly, might be experiencing glitches. Minor ones, you hope. But the thing about fly-by-wire aircraft is that they're designed, assuming the computers will work correctly. There's redundancy, sure, triple or quadruple redundant systems. But they're all built on the same basic assumption, that the electronics are trustworthy. What if they're not? What if high-energy particles are slipping through the fuselage, through the shielding, hitting memory chips and processors, causing bit flips and upsets? Commercial aircraft aren't designed like satellites or spacecraft. They don't have the same level of radiation hardening. Why would they? We're flying in Earth's atmosphere, protected by the magnetosphere, right? Except at cruise altitude, you're above a lot of that protection. And during a severe solar storm, even more radiation gets through. This is the nightmare scenario that allegedly prompted someone, somewhere, to make a call. To decide that 6,000 aircraft needed to be grounded immediately for emergency software updates. Whether that actually happened, whether it happened for exactly those reasons, I can't prove. But the fact that it's even plausible tells you something about where we are. We've built systems that are incredibly capable and incredibly fragile at the same time. And here's the kicker. That X5.1 flare on November 11th, that might not even be the worst we see this cycle. Solar Cycle 25 is still ramping up or near its peak. There could be bigger flares coming, faster coronal mass ejections, multiple CMEs hitting in succession, creating compound storms that are worse than the sum of their parts. We're playing a game of cosmic roulette, and the house always wins eventually. Now we get to the part that sounds like something out of a techno thriller. Except it might be real. And even if it's not exactly how it's been described, the underlying vulnerability definitely is. So let's talk about what allegedly happened in the wake of that November solar event, and why it matters whether the specific details are accurate or not. The claim goes something like this. In the days following the X-5.1 flare and associated coronal mass ejection, approximately 6,000 Airbus A320 family aircraft worldwide were subjected to emergency groundings or restrictions. The reason given, if you believe the whispers, was that engineers had identified a potential vulnerability in the fly-by-wire systems. Specifically, that high-energy particles from solar storms or cosmic radiation could potentially cause bit flips or computational errors in the flight control computers, leading to uncommanded maneuvers or system failures. Let me be crystal clear here. I don't have official confirmation that this grounding happened exactly as described, for exactly those reasons. The aviation industry doesn't tend to advertise when it discovers fundamental vulnerabilities in widely used aircraft. But let's examine why such a scenario is not only plausible, but perhaps inevitable given how modern aircraft work. Fly-by-wire is one of those terms that sounds futuristic, even though it's been around for decades. Traditional aircraft had mechanical connections between the controls and the control surfaces. You turn the yoke, cables pull, flaps move, plane turns. Simple. Heavy, but simple. Fly-by-wire replaced all that with electronics. Sensors detect what the pilot wants to do. Computers process that input, factor in current flight conditions, aerodynamic limits, and dozens of other parameters, then send electrical signals to actuators that move the control surfaces. It's lighter, more efficient, and allows for sophisticated features like envelope protection that prevent pilots from accidentally exceeding the aircraft's design limits. It's also completely dependent on those computers working correctly, all the time, without fail. Because unlike the old mechanical systems where you could feel the aircraft through the controls, fly-by-wire is mediated. You're telling the computer what you want, and the computer is doing it. If the computer stops working, or starts working incorrectly, things get bad fast. Now let's talk about what happens when a high-energy particle hits a microprocessor. These particles, whether they're protons from a solar event, or heavy ions from galactic cosmic rays, carry enormous amounts of energy in a tiny package. When one strikes a transistor in a computer chip, it can deposit enough charge to flip the state of that transistor. If that transistor happened to be storing a bit of data, congratulations, you just corrupted that data. If it was part of a logic circuit performing a calculation, you just got the wrong answer. This phenomenon, called a single event upset, or SEU, is well known in the spacecraft industry. Satellites deal with it constantly. That's why spacecraft computers are radiation hardened, built with special manufacturing processes and materials that make them more resistant to these effects. They're also slower, bulkier, and more expensive than commercial electronics, which is fine for a satellite, but not so great for a commercial aircraft, where weight is money, and you need lots of computing power. Commercial aircraft use commercial-grade electronics with some hardening and lots of redundancy. The idea is that if one computer glitches, you have 2 or 3 others doing the same calculation, and they vote on the right answer. That works great for random hardware failures. But what if the radiation environment suddenly gets worse? What if during a severe solar storm, you're getting SES more frequently than the system was designed to handle? What if multiple computers experience errors at the same time? Enter the JetBlue Clear Sky plunge, allegedly. The details are murky, but the story goes that a commercial aircraft experienced a sudden, uncommanded dive, 25,000 feet in seconds, passengers floating out of their seats, oxygen masks deploying, pilots wrestling with controls that weren't responding the way they should. And then, somehow, recovery. The aircraft pulled out, landed safely, and everyone walked away, with a story they'll never forget, and probably some injuries. The mystery is what caused it. There was no weather, no turbulence, no obvious mechanical failure. The aircraft was in perfect flying conditions, what pilots call CAVU, ceiling and visibility unlimited. So what happened? One hypothesis, the one that apparently scared someone enough to consider grounding thousands of aircraft, is that a cosmic ray or high-energy particle struck one or more flight control computers, causing errors that resulted in the dive. Here's why that's terrifying. Cosmic rays don't respect flight schedules. They don't care if you're over an ocean or a city. They strike randomly, unpredictably. And while most of them don't cause problems, every once in a while, one hits just the right spot at just the wrong time. Now multiply that risk by the thousands of aircraft in the air at any given moment, each flying tens of thousands of miles per year, each accumulating thousands of hours at altitude where cosmic radiation is stronger. The statistics start to look uncomfortable. If there's even a small probability of a radiation-induced flight control error per flight hour, and you're flying hundreds of millions of flight hours per year, globally, you're going to have incidents. Maybe most of them minor, maybe some not so minor. And if solar activity is increasing, if we're entering a period where the radiation environment is more severe, that probability goes up. So, what do you do if you're an aircraft manufacturer or a regulatory authority and you realize this? You have a few options. You can try to improve shielding, but that adds weight, and there's only so much you can do against high-energy particles anyway. You can improve the software, adding more error detection and correction, but that's complex, and you have to be sure you're not introducing new bugs. You can improve the redundancy architecture, but that's expensive and might require hardware changes. Or you can quietly push out software updates and hope they help. Maybe restrict some operations. Maybe ground aircraft if you think the risk is acute. And you definitely don't advertise any of this too loudly, because the traveling public might have questions. Questions like, why did you build aircraft that can be knocked out of the sky by invisible particles from space? And how long have you known about this? And what else don't we know? Fair questions, really. The broader point here isn't about one manufacturer or one aircraft type. It's about the fundamental bargain we've made with technology. We've built systems that are incredibly capable, efficient, and cost-effective in normal conditions. But those normal conditions assume a relatively stable environment. They assume cosmic radiation at historical levels. They assume solar activity within expected bounds. They assume that the electromagnetic environment is what we think it is. What happens when those assumptions break? What happens when the sun decides to throw a tantrum bigger than anything we've seen in the modern aviation era? What happens when cosmic rays get stronger or more frequent due to changes in the solar magnetic field or galactic environment? We're about to find out, and the answer might involve a lot more aircraft on the ground than anyone wants to admit. Let's zoom out for a moment and look at the bigger picture, because that November 11th flare wasn't a random occurrence. It was part of a pattern, and that pattern is something we need to understand if we want to grasp just how much trouble we might be in. The sun operates on cycles. This has been known since the mid-1800s, when astronomers started systematically counting sunspots. Every 11 years or so, the sun's magnetic field does something complicated. The field lines get twisted by the differential rotation of the solar plasma. Remember, the sun isn't a solid body. It's a ball of ionized gas, and different parts rotate at different speeds. The equator spins faster than the poles. This twists up the magnetic field like winding a rubber band, storing energy. Eventually, something gives. The magnetic field reorganizes, and all that stored energy gets released through the surface as sunspots, flares, and coronal mass ejections. This is solar maximum, the peak of the 11-year cycle. After that, things calm down again. The cycle runs its course and then starts over. Minimum, rising phase, maximum, declining phase, minimum. Rinse and repeat. We're currently in solar cycle 25, and based on observations through late 2025, we're at or very near the maximum. What does that mean practically? It means more active regions on the sun's surface, more sunspots, more flares, more coronal mass ejections, higher probability of major space weather events. And active region 4274 was a perfect example of what solar maximum can throw at us. This wasn't just one flare and done. This was a sequence, a cluster of eruptions over several days, each one major, building up to that X5.1 climax. Scientists who study the sun got very interested in AR 4274. A research paper published in December 2025 analyzed high-resolution observations of this region using advanced solar telescopes. What they found was fascinating and kind of ominous. The sunspot group showed strongly curved penumbral filaments, which are magnetic structures in the outer part of the sunspot. It showed rotation, with parts of the sunspot twisting around, and it showed strong shear motions along what's called the polarity inversion line, the boundary where the magnetic field changes direction. All of these features are signatures of magnetic stress. The field is twisted, compressed, loaded with energy. It's like a steel cable being bent and twisted until it's ready to snap. And when it does snap on the sun, the energy release is phenomenal. That's what generated the X 1.7, the X 1.2, and finally, the X 5.1 flares. Each eruption released some of the stored energy, but the fundamental instability remained, which is why multiple flares came from the same region. Here's what worries me about this. If one active region can produce multiple X-class flares over a period of days, and we're at solar maximum with multiple active regions on the sun at any given time, what's to stop multiple regions from erupting simultaneously or in quick succession? What if 2 or 3 CMEs get launched toward Earth in a row, arriving hours or a day apart? This isn't hypothetical. It's happened before, though not in the modern era. In September 1859, the so-called Carrington event involved multiple eruptions and CMEs that hit Earth in a 1-2 punch. The first one partially cleared out and weakened the magnetosphere, and the second one hit that weakened field and caused absolute chaos. Telegraph systems worldwide sparked and caught fire. Auroras were seen near the equator. Compasses went haywire. Now imagine that happening today. We have exponentially more technology dependent on electromagnetic systems. Our power grids are more extensive and more vulnerable to geomagnetically induced currents. We have satellites everywhere, from low Earth orbit to geostationary. We have GPS constellations that civilization depends on. We have aircraft in the sky around the clock. The damage from a Carrington-class event today would be measured in trillions of dollars and potentially millions of lives if cascading failures took down power grids for extended periods. And here's the really uncomfortable part. We don't know if we're building up to something like that or not. Solar physics is complicated. We can observe what's happening on the sun's surface. We can track active regions and measure flares. We can see CMEs launching. But predicting what will happen next is still more art than science. We have models, sure. Statistical models based on historical data. Physics models based on magnetohydrodynamics. But the sun is turbulent, chaotic, full of feedback loops and nonlinear behavior. Small changes can cascade into big effects. AR 4274 might have finished erupting and rotated off the visible disk of the sun, or it might have more in store for us when it rotates back around. Other active regions are probably forming as you read this. The sun is spotty right now, pockmarked with magnetic instabilities. Each one is a potential bomb. Each one could erupt with little warning. What we know for sure is that solar cycle 25 has been active. More active than some predictions suggested. Hundreds of M-class flares, dozens of X-class flares through 2025, multiple significant CMEs, several strong geomagnetic storms. The pattern suggests this cycle is robust, energetic, potentially one of the stronger cycles in recent decades. And we're not past maximum yet. The peak could last months or even a year or more before activity starts to decline. That's a lot of time for something bad to happen. A lot of opportunities for the right combination of factors to come together. A fast CME, an Earth-directed trajectory, multiple eruptions in sequence, a weakened magnetosphere, high cosmic ray flux. Any one of those alone might be manageable. All of them together? That's when you start worrying about whether the systems we've built can actually handle what's coming. And there's another angle to consider. Some researchers think that the solar magnetic field itself might be changing in ways we don't fully understand. The sun's overall magnetic field has been measured to be weaker in recent cycles than it was mid-20th century. A weaker solar magnetic field means less protection from galactic cosmic rays, the high-energy particles that come from outside our solar system. More cosmic rays hitting Earth means more radiation exposure for aircraft, satellites, astronauts. It means more potential for single-event upsets in electronics. So we're potentially facing a double whammy. More solar storms during solar maximum, and more background cosmic radiation due to a weaker solar field. The radiation environment is getting worse from both directions. And our technology is getting more sensitive at the same time, with smaller transistors and more complex systems that have more opportunities for things to go wrong. None of this is to say that catastrophe is inevitable or imminent, but it is to say that we're playing with forces we don't completely control or understand, using technology that wasn't designed with worst-case space weather in mind, and the worst case might be coming sooner than anyone wants to think about. Now, we need to talk about something most people have never heard of, but which might be the most dangerous aspect of this whole situation. Ground-level enhancements. GLEs for short. And if you're thinking that name sounds ominous, you're right. Most of the time when we talk about solar storms, we're talking about X-rays, extreme ultraviolet radiation, and charged particles like electrons and protons that interact with Earth's magnetosphere and upper atmosphere. That stuff causes auroras, radio blackouts, satellite problems, maybe power grid issues if it's severe enough. But it mostly stays up in space, or the very upper atmosphere. Ground level, where we live and work, is pretty well protected by the magnetosphere and the thick blanket of atmosphere above us. Except when it's not. Ground level enhancements are rare events where solar energetic particles, particularly high-energy protons, are accelerated to such high speeds by the magnetic fields in solar eruptions that they can penetrate all the way through the atmosphere to ground level. These aren't just charged particles. These are relativistic particles, moving at significant fractions of the speed of light, carrying enormous amounts of energy. When a GLE occurs, neutron monitors at ground level, which are designed to detect cosmic rays, suddenly spike. That's because the incoming high-energy protons are hitting atoms in the upper atmosphere and creating showers of secondary particles that cascade down to ground level. It's like cosmic shrapnel. And if those particles are energetic enough, they don't just trigger neutron monitors. They can penetrate aircraft fuselages, building walls, even some amount of shielding. They can hit electronics directly. The scary thing about GLEs is that they're unpredictable and they happen fast. When a particularly powerful solar eruption occurs, especially one with a strong shockwave in the corona, it can accelerate protons to GLE energies in minutes. Those particles then travel to Earth along magnetic field lines, arriving sometimes in less than an hour after the flare. Faster than the CME itself. Faster than most warning systems can react. And here's where it gets really interesting. GLEs are associated with the biggest, most powerful solar eruptions. X-class flares on the high end. Fast CMS. Strong shocks. The exact kind of events we're seeing more of during this solar maximum. The November 11th X 5.1 flare was certainly powerful enough to potentially generate energetic particles at GLE levels. I don't have confirmation that it did, but it's the kind of event where you'd check the neutron monitors carefully. Why does this matter for aviation and electronics? Because high-altitude commercial aircraft are flying through the upper part of the atmosphere, where the particle flux during a GLE is much higher than at ground level. They're above most of the atmospheric shielding. Pilots and flight attendants during a severe GLE can receive radiation doses equivalent to several chest X-rays in a matter of hours. That's a known hazard, monitored by regulatory agencies, though not widely advertised to passengers. But the radiation exposure to humans, while concerning, might not be the biggest problem. The bigger problem is what those particles do to electronics. A high-energy proton slamming into a microprocessor can cause a single event upset, just like we discussed earlier. But during a GLE, you're not getting occasional random hits. You're getting a shower of particles. Multiple hits per second, potentially. Hitting multiple systems simultaneously. Commercial aircraft electronics aren't radiation hardened to spacecraft levels. There's some hardening, sure, some shielding, but it's designed for normal cosmic ray background, not for GLE conditions. If you suddenly increase the particle flux by orders of magnitude, you're outside the design envelope. Computers start experiencing errors more frequently than their error correction algorithms can handle. Systems that were never supposed to fail at the same time might fail at the same time. This is where the clear sky plunge scenario starts to make a horrible kind of sense. If an aircraft was flying at high altitude during a GLE or a sudden burst of high energy particles, and if multiple flight control computers experienced SE use simultaneously, the voting systems might fail. The computers might disagree on basic facts like altitude or attitude. The autopilot might make incorrect decisions. In the worst case, the aircraft could enter an uncommanded maneuver before the pilots could diagnose and recover. And here's the thing that really keeps me up at night. We don't have good real-time monitoring for GLEs at aircraft altitudes. Neutron monitors are mostly on the ground. Some aircraft carry dosimeters for measuring radiation exposure, but those are for tracking cumulative dose to crew members, not for warning of sudden events. By the time anyone realizes a GLE is happening, aircraft could already be flying through it. The European Space Agency and other organizations have been sounding alarms about this. Space weather monitoring has improved dramatically in recent years, but there are still gaps. We can detect flares immediately when they happen. We can track CMEs as they propagate. But predicting which eruptions will generate GLEs and how severe they'll be and exactly where they'll hit, that's still very much a work in progress. There's also the question of galactic cosmic rays. These are particles from outside our solar system, accelerated by supernovae and other violent events in the galaxy. They're always present, always bombarding Earth, always causing low-level radiation effects. The solar magnetic field usually helps deflect some of them, which is why cosmic ray flux goes up during solar minimum when the sun's field is weaker. But during solar maximum, even though the sun's field is stronger, you get more solar energetic particles to compensate. The net result is that the radiation environment at aircraft altitudes varies in complicated ways depending on solar activity, galactic cosmic ray flux, Earth's magnetic field configuration, and where you are on the planet. Flying polar routes exposes you to more radiation than equatorial routes because Earth's magnetic field funnels particles toward the poles. Flying during solar storms increases exposure. Flying at higher altitudes increases exposure. It all adds up. For decades, we've treated this as mainly a health concern for frequent flyers and flight crews. And it is. But increasingly, it's also an electronics concern. As chips get smaller and more sensitive, as we pack more computing power into aircraft systems, as we depend more, critically on those systems working correctly, the vulnerability to radiation-induced errors goes up. Nobody wants to talk about this publicly, because it sounds like fear-mongering. It sounds like we're saying modern aircraft aren't safe. That's not quite right. They're safe under normal conditions. They're engineered with enormous safety margins and redundancy. But are they safe under severe space weather conditions that we haven't experienced in the jet age? Are they safe during a GLE event that's stronger than anything in the historical record we used to design them? Honestly, we don't know. And we might be about to find out. Some theorists propose that human power grids operating at 50 Hz or 60 Hz across continents might be influencing near-Earth space in ways we are only beginning to grasp. These vast electrical networks hum constantly, sending energy through the veins of modern civilization. But in doing so, they create electromagnetic harmonics that leak upwards, subtly interacting with the upper atmosphere and even the magnetosphere itself. Proponents of the tech trigger hypothesis suggest that these harmonics could disturb the normally stable belts of trapped radiation surrounding our planet. When these belts are nudged, energetic particles, protons, electrons, and other charged fragments can be knocked loose, sometimes cascading toward Earth with unpredictable force. These particles do not announce themselves with fireworks or visible light. They arrive silently, and yet, for aircraft flying tens of thousands of feet above the surface and satellites spinning overhead, their effects could be catastrophic. In this view, human infrastructure is no longer passive in the cosmic equation. Instead, we might be, unwittingly, prodding the cosmic hornet's nest, stirring a storm that was once the domain of our star alone. It is a frightening thought. The same grids that power our homes, hospitals, and data centers may also be subtly agitating the radiation belts, sending invisible bullets toward our most fragile technology. Other analysts raise questions about the effectiveness of our natural shields in this increasingly electrified and electronically noisy world. Earth's magnetosphere and thick atmosphere have long served as reliable buffers against cosmic rays and solar energetic particles, neutralizing most threats far above the altitude of commercial aircraft. Yet when this shield is combined with the electromagnetic emissions of human activity, some researchers warn that it might not be as impermeable as we assume. If even a temporary thinning occurs, a momentary vulnerability in a system we take for granted, it could allow high-energy particles to reach sensitive electronics in airplanes or satellites. Imagine a plane cruising above the Pacific when an invisible surge hits its fly-by-wire systems, flipping bits, scrambling software, and sending avionics into chaos without warning. The threat is not constant, not guaranteed, but the mere possibility of such an event forces us to reconsider the boundary between cosmic hazards and our own technological footprint. Traditional space weather models, however sophisticated, may not capture these subtleties. During periods of solar maximum, when the sun's magnetic fields twist and writhe unpredictably, isolated energetic particle events known as ground-level enhancements, or GLEs, can occur. Unlike the dramatic, headline-grabbing solar flares or coronal mass ejections, GLEs can flood the atmosphere with radiation particles quietly, often without any obvious precursor. These events are rare, and their unpredictable nature makes them difficult to incorporate into risk assessments for aviation and satellites. Operators might assume a calm sky, yet particles can surge through, striking electronics at high altitudes, causing bit flips, single event upsets, or even full system resets. For decades, these events have been statistical outliers, almost curiosities in space physics papers. But in an era of digital fly-by-wire systems and mega constellations of satellites, even one isolated event could trigger cascading failures. Some observers take this line of thought further, contemplating the role of external cosmic actors in stirring the sun itself. The interstellar object known as 3I Atlas has become a focal point for speculation. As it passes near the sun, some propose that its magnetic field, or even its gravitational influence, could interact subtly with solar plasma or stressed sunspot regions. In this scenario, a region already on the verge of instability could be tipped past a threshold, triggering a flare or a cascade of solar events. Supporters of this interstellar activator hypothesis admit that no peer-reviewed study confirms such a chain of causation, yet they point to intriguing coincidences. Rising solar instability, an uptick in flare frequency, and recent anomalies in cosmic ray measurements. Could this object, just passing through our solar neighborhood, be nudging the star itself? The data remains circumstantial, but the implications are hard to ignore. In parallel, conspiracy-minded observers scrutinize the unprecedented grounding of 6,000 Airbus A320 jets. They question whether this action was a simple precaution or based on early knowledge of an imminent threat. If the firms truly believed their electronics were vulnerable, some suggest they had access to radiation measurements or predictive models unavailable to the public. By quietly pulling planes from the skies, engineers and executives could have been buying time, not only to patch software, but also to avoid mass panic. From the outside, this appears prudent. To some, it looks like a shadowy, preemptive measure, hiding uncomfortable truths. The scenario raises uncomfortable questions about transparency, decision-making, and the intersection of technology, science, and corporate discretion. Skeptics, of course, remind us to temper our imaginations. They point out that while human infrastructure does emit electromagnetic noise, evidence that it destabilizes the magnetosphere is minimal. Cosmic ray strikes on electronics, they note, are usually stochastic and isolated, rarely producing systemic failures. They warn against letting interesting hypotheticals become alarming narratives without evidence to support them. Maintaining a distinction between what is scientifically established, what is plausible but unverified, and what is purely speculative is crucial. Otherwise, curiosity risks evolving into paranoia, turning a fascinating story into a sensationalized warning. Yet even skeptics acknowledge that rare events can have outsized consequences. Aviation and satellite systems, so integral to modern life, are more complex and interdependent than many appreciate. A single bit flip in the right or wrong place could cascade into navigation errors, communication failures, or even temporary power outages. The margin for error is thinner than we might imagine, particularly under conditions we cannot fully control or predict. Some part of the risk is unavoidable, but part of it is a function of human activity interacting with cosmic forces in ways we are only beginning to recognize. In contemplating these possibilities, we also confront a philosophical tension between certainty and uncertainty. We cannot definitively prove that 3I Atlas is influencing the Sun, or that power grid harmonics are perturbing radiation belts. We can only point to coincidences, patterns, anomalies, and unanswered questions. This tension is uncomfortable, yet it is where science often lives, in the gray space between known facts and unexplained phenomena. It is a space that demands both caution and imagination, a space where inquiry must proceed without panic, but with attentive curiosity. Ultimately, the story of our sun, our technology, and the subtle interplays of cosmic forces is a story of humility. We have built sophisticated systems that shuttle people across the globe, orbit satellites to monitor every corner of the planet, and communicate instantly across continents. Yet, for all our ingenuity, a single, invisible surge of particles, or a minor destabilization in a solar region, could remind us how small and interconnected our systems truly are. It is not only a question of science, but of perspective. Recognizing our fragility without succumbing to fear, appreciating the potential consequences without overstating the certainty. As you consider these ideas, remember that vigilance, preparedness, and humility are the best defenses. There are steps that can be taken: better radiation shielding, improved monitoring, contingency protocols, but uncertainty cannot be eliminated entirely. The cosmos does not negotiate, it does not pause for human schedules, and it often acts with a disregard for convenience or expectation. So we watch, we measure, we plan, and we wonder. The next surge may be quiet and unnoticed, or it may announce itself with sudden, dramatic consequences. Would you rather ignore the patterns now and hope for the best, or recognize the tension, prepare, and remain alert to the subtle signals that may presage a disruption unlike any other? In the end, that tension between the seen and the unseen, the measured and the speculated, is where the real story unfolds, and it is where we must pay attention. For once the cosmos moves, it does so without waiting for permission or explanation. This expansion reaches approximately 1,000 words and maintains the narrative flow, tone, and investigatory style you requested. Some satellite operators report that the solar storm season of 2025 has already triggered multiple disruptions in low Earth orbit. These reports describe unexpected errors in instrument readings, sudden power resets, and precautionary shutdowns to protect delicate electronics whenever the sun showed signs of a flare, or when coronal mass ejections were detected heading Earthward. These incidents demonstrate that the threat is not limited to aviation, but extends to the satellite networks we rely on for communications, navigation, weather monitoring, and global data systems. Other agencies caution about increased atmospheric drag on satellites caused by geomagnetic storms. They explain that when the upper atmosphere heats and expands during a storm, satellites in low orbits dip into denser air layers and encounter more friction. They warn that this reduces orbital lifetime, risks uncontrolled re-entry, and threatens to shorten the useful lives of satellites. They emphasize that such effects may degrade global internet connectivity, Earth observation capabilities, and the very infrastructure underpinning modern commerce and security. Some researchers describe how radios, GPS, and high-frequency communication networks become unreliable during solar storms. These communication failures ripple outward. Airline navigation, maritime shipping routes, emergency response systems, and even power grid synchronization may be disrupted. They argue that if a powerful flare or CME hits during critical operations, say during mass flights, global shipping cycles, or power peak demand, the consequences could cascade quickly from technical glitches to widespread chaos. Other scientists note that beyond Earth, human missions to the Moon, Mars, or beyond are becoming increasingly risky again. They highlight that spacecraft and astronauts outside Earth's protective magnetosphere face direct exposure to solar energetic particles and cosmic rays. They warn that radiation shielding designs conceived decades ago may not suffice under the emerging solar regime of 2025 and onward. They urge space agencies to revisit radiation models and upgrade protection before launching crewed missions beyond orbit. Some technologists point out that as we build mega constellations of satellites for global internet coverage, we might be stacking fragility into our global infrastructure. They argue that having thousands of satellites in LEO increases the chances that one or more will be disabled by a solar storm, potentially triggering a chain reaction of system failures. They question whether humanity is making resilience or vulnerability at scale, and whether some assumed redundancy in design might really be systemic fragility. Other voices insist that predicting solar storms remains extremely difficult. They remind that while models have improved, forecasting the timing, strength, and direction of coronal mass ejections or particle showers often fails. They caution that even leading agencies rarely have more than a few days lead time, sometimes only hours before a storm hits. They stress that without significantly more advanced early warning systems, shielding protocols, and global coordination, we remain vulnerable to sudden, unpredictable solar outbursts. Some planners suggest that investment in radiation-hardened electronics, redundant communication networks, and hardened infrastructure might help. They propose putting more satellites into higher orbits, reinforcing power grid shielding, equipping aircraft with better radiation monitoring, and creating contingency flight rules for solar storms. They argue that the cost of precaution now may save trillions in economic losses, not to mention lives, if a major space weather catastrophe strikes. Some visionaries propose using artificial intelligence and machine learning to forecast solar activity more accurately. They describe research underway in 2025 aiming to analyze decades of solar data, sunspot evolution, magnetogram patterns, and cosmic ray fluxes to predict when the sun might flip into high activity mode. They hope these tools will give hours or even days of early warning, enough to ground flights, power down sensitive systems, or reposition satellites. They also caution that these predictions will never be perfect, but even a modest lead time could improve readiness enormously. Some of you may be wondering whether all this talk of cosmic threat and fragile infrastructure is just alarmism. Others may be quietly checking their phones and imagining satellites falling silent, planes grounded, blackout zones on Earth. I urge you to hold those thoughts. I invite you to imagine a world a few hours from now, under a global solar eruption, where the screens go black, navigation goes haywire, satellites vanish from the sky like extinguished stars. I ask you to consider this. In the next solar cycle, we may not have a choice between being ready or unready. We may already be behind schedule. I leave you with one final question. When the next wave of cosmic storms rolls in, will our system of wires, silicon, and steel bend or break?